Well, welcome again to our tutorial on graph neural networks, learning representations of robot team coordination problems. My name is Matthew Gomble. I'm an assistant professor at the Georgia Institute of Technology in the School of Interactive Computing. I've been here for 4 years, and I'm very proud to be able to do this workshop with an amazing PhD student, Jae-Eun Wong, who joined me in my first year. And he's going to be wrapping up this year defending, defending his PhD thesis on this very topic. He's an absolutely amazing student, and we're going to divide up the workshop or the tutorial today. Where the first half, for 90 minutes or so, I will give a more lecture-based overview of graph neural networks. How do we make them work for scheduling problems? And then Jae-Eun is going to follow that up with the Google Colab tutorial on how to get these systems to actually work, give you some code to play with, some example problems, and hopefully by the end of today, you'll be well on your way to solving these problems with graph neural networks on your own. Again, please feel free to interrupt me at any point if you have any questions. We do have a lot of material to get through, so I will try to keep us on time. But I definitely want this to be an engaging, interactive tutorial as much as it's beneficial. For my first half portion, we're going to go over multi-robot coordination problems in general. What are they? How do we classify them according to some taxonomy of challengingness? Then we'll go into graph neural networks, give a general overview of these modeling techniques. And we'll talk about how do we apply these to solving multi-robot coordination problems. How do we both design them and optimize them in order to coordinate human-robot teams? And then finally, we'll go over a little bit of our ongoing and future work, wrap up with some challenges and motivation for the future. Then we'll take a short break for anyone to step away if they need to take care of anything. And then we will come back just after a few minutes, and Jae-Eun will pick up with the Google Colab tutorial. So let's start with multi-robot coordination problems. Resource optimization problems are present in almost every facet of our daily lives. Resource optimization can affect airplane manufacturing for deciding which human or robot team member needs to perform which tasks on an aerospace fuselage, but it also can expand into a larger set of just the logistics of how do you get all of the parts to the factory from across the world with an integrated globalized supply chain. Patient appointment scheduling and healthcare is very challenging. I'm sure most of us have experienced the challenges of figuring out how do we get an appointment. There are also challenges in the dynamic sense of running an emergency room, making sure that you have the right doctors and staff to take care of emergent patients coming through who need surgery for trauma, and then setting up all the visits that one would need after staying in the hospital for a while. Amazon has certainly become the forerunner in logistics of e-commerce and delivering packages to your home in the same day in some cases. And then airline crew scheduling is also a significant challenge, and the stochasticity there involving whether your plane is going to break and you have to replace it with another plane to get your customers to where they need to be, and also making sure the crew are available and that they haven't exceeded their limitations for the number of hours they're awake and working. We're going to focus today on a couple facets of this general landscape. First is the coordination of multi-robot systems, where you can think of teams needing to be able to communicate or coordinate their activities, perform task planning. Specifically, we'll say task allocation and scheduling. Task allocation is the process of assigning a worker to a job, and scheduling would be ordering that job through time. And then we can also think about motion planning. Once these agents have their task allocation, how do they then move through the factory in a way that doesn't collide with anyone else? Motion planning will be out of scope for today, though it is a very important and interesting problem. And researchers are focused somewhat on integrated task and motion planning. Leslie Cabling, for example, has been pursuing that work. But today we're going to focus on task allocation and scheduling. And then we're going to, at the very end, we'll cover a little bit about aircraft plane maintenance scheduling is a very challenging instance of scheduling problems in which you have a great stochasticity, and you actually don't know what tasks need to be performed a priori. You actually have to decide that. And that's very much in contrast to typical job shop scheduling, where you're given a queue of tasks to be performed with their associated constraints. So now we need to decide what has to happen and hedge about the stochasticity of when planes may break, because ideally you're fixing the parts before the plane breaks, not waiting until after that happens, when you're not able to control when the plane is going to go down. In general, we have to coordinate a finite number of resources to accomplish a set of tasks as efficiently as possible. And efficiently here is going to be a domain-specific reasoning. There has been a revolution in aircraft assembly that has opened up some of these questions for how do we dynamically coordinate robots. Traditional aircraft assembly use large gantry-style robots, systems that are the size of a house. And you put in a part of a plane, you put it in, and the work gets performed. It's relatively deterministic, and it takes a very long amount of time. But with a push, with advances in robotic hardware that are allowing us to integrate mobile robots around a factory and reconfigure the factory itself, we actually have the question of how do we dynamically re-optimize from day to day or from part to part what each member of the team should be doing. These challenges are likewise present in warehouse automation, increasingly with automotive manufacturing, where we see customers demanding made-to-order parts. Rather than just having a one-size-fits-all model for what we're building, more and more of US manufacturing in particular is moving to every customer has their own specific design for a part, and that requires the ability to dynamically decide which of my workers are going to do which tasks and when and where to make sure that everyone has what they need. And the COVID-19 pandemic has also, I think, accelerated the adoption of robotic equipment that then necessarily needs the ability to have something or some system coordinate their activities. And we are doing work in our lab looking at research in multi-robot systems in terms of how do these systems communicate if they live in a decentralized world, need to share information, how do we form their teams, look at task scheduling and routing. And we also try to work with our partners to look at real-life applications. We have partners, for example, with Lockheed Martin that we're working with for predictive maintenance, but there are many others, Amazon for warehouse automation and more. Our focus on assembly manufacturing today will be deciding who, the assignment of tasks to robots, and then when, the scheduling of tasks for each robot ordered through time. The key challenges here are going to be the temporal constraints on task completion time and the relationships between those tasks. For example, we say wait constraints or deadline constraints. One task has to come before another for some duration, or you have a finite amount of time, a deadline, until you complete a certain set of tasks. And we also consider spatial or resource constraints. This could be robots might need to share a specific tool to perform a job, or they need to negotiate a shared space. So no two robots or a human robot can be in the same place at the same time. Certainly we don't want a human robot and co-occupying the same space, because the human will typically lose in that engagement. And Corsaw et al. Developed a really nice taxonomy that was out in IJR in 2013, building upon Gürke taxonomy a few years earlier. And tasks we can think of as being divided into single robot tasks versus multi-robot tasks. That's how many robots do you need to complete each discrete unit of work. We can think about robots likewise as being able to do one task at a time or multiple tasks at a time for robot type. And then we can think about instantaneous assignment. This is more of a matching problem of I'm going to assign robots to jobs just now, so every robot gets, say, one job, and I don't have to worry about the future. Versus time extended allocation is I want to schedule all the way into the future, so robots will have a queue. Each robot will have a queue of tasks ordered. And then for each unit of tasks, we can think about, say, an elemental task where a robot performs a task in isolation. It doesn't have to consider other tasks. We can think about simple tasks, where maybe there is some kind of like deterministic decomposition of tasks that need to be performed, and multiple robots are needed to accomplish each unit of those works. Compound tasks kind of grows in complexity, where maybe there's a task that has multiple facets, and depending on how you divide it up, multiple robots need to be able to work together to accomplish the task. And then complex tasks get into more of a planning aspect, where tasks can be decomposed many different ways So for example, this comes up in disaster response, where you might imagine that a fire truck needs to be able to get to a burning building, and there are two routes to get to that building. One is blocked by some rubble, and maybe you could have a bulldozer come and move the rubble out of the way and then have the fire truck go to the disaster, or the fire truck could go a different route, but it takes much longer. So now I have to decide which route do I take, and that entails more work to be performed. So that kind of decision about how do you divide the task of getting from point A to point B might involve other robots and have different temporal parameters. So in the first bit of our talk, we're going to focus on time extended scheduling, where we have to schedule multiple tasks to each robot, thinking into the future with a finite horizon. Each of our tasks will be able to be accomplished by a single robot, and each robot can do one task at a time, and we're going to focus on simple tasks. Within this, we will have cross-scheduled dependencies. For a single task, single robot time extended allocation. Cross-scheduled dependencies arise because what one robot does affects another. If two tasks have a weight constraint relating them, one task has to come before the other, and you have two different robots doing those tasks, then the second robot has to wait on the first robot to finish its task. So this means that we can't just do some simple divide and conquer strategy. We actually have to look at an integrated schedule to make sure that each robot has what it needs in the right time. We're going to make a couple of assumptions here. First is that the robot task proficiency is known beforehand. So we know what robots are capable of. And to the degree to which all of these techniques can be applied to human work, we also want to think about how humans, you can also characterize what humans are capable of. Maybe there's certification. So you can have a welder or somebody who can do riveting. The problem is that you do have to pay attention to privacy considerations. For example, in states with strong worker protection laws or collective bargaining agreements with unions, you typically cannot collect data on how quickly each individual person performs tasks. So you have to reason about it in the aggregate sense. And also within aerospace manufacturing, it's reasonable to assume that the travel time that a robot will require to travel from one location to another is much smaller than the task duration. So it takes about maybe 10 to 100 times longer to perform a task than it takes to travel between the tasks. So we're going to assume that travel time is not important for this application. Let's get into defining a problem. Real robotics is quite hard. So I worked with my former PhD advisor. We had a startup that we spun out to apply some of our work to this coordination of multiple robots and humans working together to build the aft fuselage of a 777. This was part of the fully autonomous upright build project with Boeing, just north of Seattle, Washington. And here's a video of it working in action. It's quite impressive to watch these about 6 meter tall robots performing these operations. Mathematically, we could define this as an integer program where we decide for a set of tasks, say drilling a hole or fastening that hole, each task will be labeled I or J. And Xij decides whether task I comes before or after task J. Task I coming before task J means that Xij would be 1. We have complementary task allocation variables for deciding which agent A will perform task I, which is 1, if that assignment is true. We also have continuous variables for the start and finish time of each task. In general, you want to minimize the make span over the overall process duration. And then you'll also have some application-specific criteria that we'll cover a little bit later. Every agent will be assigned one task. Every task will be assigned exactly one agent. We have weight or precedence constraints saying that the finish time of one task, Fj, must come before the start time of a later task by some unit of time, W sub ij. Then we assign the ordering of tasks assignment accordingly. Deadline constraints saying that some tasks have to be completed within the start of another task. For example, in composite placement for aircraft, you have a finite amount of time to work with the composite material after you take it out of a refrigerator before it warms up and becomes unworkable. Example of weight or precedence constraints is if you're painting a house, and you apply the first coat of paint, you need to wait some hours before you apply the second coat of paint. Every agent will be able to work at a unique rate, C sub IA. Agents will execute tasks in series, so you have to do one thing at a time. And then finally, no two robots or workers can use the same physical location at the same time. If you'll note that I'm using these big M formulations for this integer program, I don't have time to go too much into this formulation, but generally you would define this as some kind of polynomial program, but you can use this big M trick to help turn on or off constraints and be able to use it, create the formulation so that it's integer in your unknown assignment variables. Well, the real challenge here is that we don't know the optimal ordering of tasks, and the number of tasks that we have is something on the order of hundreds to thousands, where we might only have tens of workers. And so that factorial ordering problem is much more of the computational bottleneck. So in some of my prior work, I developed a novel sequencing test to determine, given an assignment of who will do what, will you satisfy your temporal and spatial constraints? This was a sufficient but not necessary test that I developed, working with my colleagues Ron Wilcox and Julie Shaw when we were back at MIT. And we would simply do this kind of worker balancing heuristic for deciding who's going to do what, and then call our analytical sequencing test to determine if that would satisfy our scheduling constraints. This approach was called Tertio. And we could iteratively find task allocations, who does what, and then determine if we can order those tasks in time according to some heuristic. And if we could, the schedule was satisfied according to what the manufacturer needed, we would dispatch the schedule. And we could do this within a simple temporal network, which we'll revisit later, that does preserve flexibility so that the solution isn't brittle if things go slightly differently than we expected. So it worked well. We found it for computation time versus the number of subtasks, or just the smallest unit of tasks that we had, we could scale to 1,000 tasks in the order of approximately a couple of minutes, whereas prior approaches would time out at an hour, at most 100 tasks for a heuristic approach. And then we would also look at green being a genetic algorithm and black being solved by Gurobi, an exact approach. We also looked at the number of problems solved. Our approach was able to achieve find feasible solutions for all the problems within our data set. We're also near optimal, finding solutions within 10% of optimal for the problem sizes that we could test, because optimal is hard to achieve once you scale beyond about 5 robots and 10 and 30 tasks. So maybe you can get that up to about 50 now. And then what was really cool is that we applied this to some problems at Boeing. Jason Herrera took our solution Tertio and showed that on a wing spar assembly problem, that the make span our approach generated was about 20% better across a range of the number of agents against some proprietary software, Aurora. So we developed our startup, delivered some software to Boeing, and became a silver vendor, which was kind of fun. But it wasn't just as easy as delivering them some code. Unfortunately, it still requires extracting domain expertise. If you remember in the mathematical program formulation, I said we wanted to minimize the make span, but there's also a lot of other terms, that G of other terms, the ad hoc criteria that you want to optimize for. At Boeing, one example was that you want to minimize the number of changes from one schedule to the next, because every change in a schedule due to a dynamic replanning need requires printing of a lot of paperwork and then telling everyone how things are going to change. So that's some ad hoc criteria that you want to minimize. So to figure that out, you have to go and interview domain experts, figure out how they handle it. I've had experience with the Navy, healthcare, manufacturing, and working with NASA. And across all these domains, what you find is that the researcher, in this case myself, would have to go interview those domain experts, bring back their knowledge, spend a lot of time and money to tweak your software, sometimes completely reinventing your approach, and then delivering a one-off solution that wouldn't be useful for anyone else ever again. And manually extracting this knowledge is labor intensive and often gives an inaccurate representation of the decision-making process. And this application-specific nuances make it impossible to scale the expertise of the researcher. So we can think this across a variety of approaches. Heuristic approaches almost by definition require domain expertise, even though they are computationally lightweight. Exact solvers may be able to produce an optimal schedule, but they're very computationally expensive and often still need a heuristic to warm start them if you're going to try to get an initial guess for your branch and bound search in order to get a solution. We can use meta heuristics like genetic algorithm or simulated annealing that are often still used in scheduling, but randomly generating the solutions to create the population for your genetic algorithm, most of those randomly generated solutions will be not feasible due to your temporal and spatial constraints. In practice, I've seen that be 80 to 90% of your population is infeasible. So you still need heuristics, and then they're also quite slow. Well, maybe learning could help. Could we figure out the right learning architecture and optimization approach so that a general purpose learning system could learn the ad hoc reasoning that it needs for each of these domains? So that's been my vision. That I've wanted to do is basically just create a bunch of robots to go out and do my bidding for me, or just to automate me. The three critical challenges that we're going to tackle today are: one, how do we learn the right features of scheduling problems for our machine learning algorithms? Two, how do we learn a policy with application-specific reasoning in the objective function? And then how do we learn problem size agnostic reasoning so that we can scale up to very large problem sizes? And we're going to do that with graph neural networks. So we've gone over multi-robot coordination problems. Now we're going to introduce graph neural networks, and then we'll cover how do we then apply them to solve these problems and some ongoing work. Features. Machine learning performance is all about getting the right feature representation. And there was a really nice innovation of convolutional neural networks for image classification to decide if they're a dog, a cat, a school bus, or an ostrich within an image, reasoning just from the pixels. And these convolutional neural networks were able to achieve outstanding performance by developing an approach that had local connections, shared weights across the convolutional filters, and then having pooling layers, max pooling layers, and then having this hierarchical structure that was very advantageous. And this came about, in approximately 2012 with AlexNet. Jeffrey Hinton and Jan LeCun were both working with their students at this time, although the technology had been there in some form or the other for decades. It really came all together in this confluence of events about 2012 with ImageNet. Now, a challenge is that while a convolutional neural network is effective for representing learning in Euclidean space, it's being used in autonomous vehicles for figuring out what is around you, what cars are around you, what street signs do you see. You can imagine that it could technically be applied to any problem with a fixed matrix representation, but how do we do this for scheduling? What is an image of a scheduling problem? A lot of real-world problems consist of data in a graphical form, even a dynamic graph, rather than just pixels in a way that a human eye can interpret that information. And so it doesn't really make sense to apply convolutional neural networks to these graphs. So instead, we're going to build a model using computational models, and there's been significant developments in extending deep neural networks to non-Euclidean data, such as graphs and manifolds. And prior work has sought to formulate appropriate model architectures for learning of graphs, which gave birth to the graph neural network family. It goes back to Scarcelli et al. In 2009. We have many other authors contributing to that in the years since. It's important to think about first a propagation module in these networks that's used to propagate information between nodes along the edges within the graph, so that the aggregated information can capture both the feature and the topological information of our graph. Then we'll have a sampling module that could be used for large-scale graphs, where maybe you don't reason about everything within the graph, every iteration. We can have pooling modules as well, just like in graph neural and convolutional neural networks, to obtain high-level, overall, the gestalt of the graph and embedding to represent that. We will do the same at first through averaging, and then later we'll actually explicitly develop a graph embedding node that we call a state aggregation node. So these graph neural networks are going to generalize deep learning to capture structural information and data, representing, in our case, how robots and tasks are all related to each other. Beyond scheduling, there's a broad application of these systems, from modeling biological systems, chemical biological processes, molecules, social networks, and recommender systems. And you can even think about these systems being used to figure out control laws for articulated robotic systems. And the quintessential difference you're going to see here is in deep neural networks, you might want to use to be able to predict a research area for a given paper. You might have input features such as the raw text of a paper, pass that through fully connected layers, and then output some classification for what the paper is. And you'll do this independently for multiple papers. But with a graph neural network, what you're going to do is you're actually going to reason within these layers about how all of the papers relate to each other within a community of interconnected papers, where edges between these papers are going to denote information such as where they published in the same conference or the journal. And you can build up almost a social network of papers in that sense. And these relations are going to capture the important structural information that we want to exploit. We can specify graph types and scales. So graphs can be undirected, as you may already know. We can also think of graphs as directed. There could be undirected and directed components to the graph. And we can also have weighted edges as well, which will be important for our scheduling problems, where the weights of the edges will denote temporal constraints for how soon after one task another task can be performed. And then typically we'll have directed weighted edges. And as a requirement for our simple temporal networks, they will be directed and acyclic. In structural scenarios, the graph structure is often explicit. That'll be in the case of our scheduling problems, such as applications for looking at like protein folding or trying to predict missing nodes within a graph, for figuring out how art and culture might be interrelated. You can actually define the entity, you know what it is, and then you want to be able to predict something about this existing graph. Or in social networks, Facebook may use it to predict, is there a missing friend that you and I might share, but that person is not currently a member on Facebook? But we can also think about non-structural inheritors where we want to find the graph structure itself. We won't really go into this too much today, but I just want to throw it out there. That people, for example, in computer vision, might want to be able to identify elements within a scene and then create nodes for the different objects and edges relating how those two things are working together. Something is on top of another, something in front of something else, and then be able to do scene understanding or captioning by first inferring what's in an image and then inferring the graph relating those elements within that image, and then using that to then comprehend the image. We will go into both homogeneous and heterogeneous graph neural network formulations. And importantly, homogeneous graphs assume that all nodes are the same. This works well for a single robot scheduling problem, or if you have homogeneous robots, where basically every node in your graph is just going to be a task. But heterogeneous graph neural networks actually allow you to think about green nodes, for example, being tasks, yellow nodes being robots. You can also have other nodes to represent resources or tools that need to be used. And we'll also look at state aggregation nodes, which we'll explain a little bit later, that allow you to look at more complicated or rich ways to express these coordination problems. We will kind of have a mix of static and dynamic graphs within our discussion today. A static graph is when the input features or topology of the graph would not vary with time, and the dynamic ones would vary with time. And the time information should be carefully considered in dynamic graphs. When we say dynamic graphs, what we mean is that when we take in a scheduling problem, we don't know which robots are going to do which tasks and how those tasks will be ordered through time. So we're going to set this up as a markup decision process, as we'll see later, where our actions are going to be to dynamically change the graph to enforce ordering and assignment in order to make sure that we can get a feasible schedule at the end of the day. But with any one time slice, the graph itself will be static. Unfortunately, there's not like a clear classification criteria for what a small or large graph might be. The criterion is still changing with the development of computation devices, speed and memory availability for GPUs. We do need a lot of virtual RAM to be able to run these systems. But we can think about, for example, the adjacency matrix in a graph, Laplacian of the graph. The space complexity is going to be O of the number of nodes squared. And we cannot really store that if it gets too large. And so once it gets too large, we can regard the graph as large scale. And then we would need to do some kind of divide and conquer method to look at one part of the graph at a time, or do some kind of sampling-based method to handle the size of that graph. And just including, for completeness, definition of the graph Laplacian L being the degree matrix less the adjacency matrix. And we can consider an L-layer graph convolutional neural network. We're going to stack graph convolutional layers as you might have for a CNN, with a hidden size, the number of features in your hidden size H, running on an in-node graph. Storing the intermediate hidden states requires O of NLH memory, easily exceeding one GPU's capacity with large N, for example, in the millions or even billions of nodes and edges in some of the graphs that we might be able to enumerate. And so one aspect that you can handle with this is to do mini batch training with only neighborhood sampling. We're only looking at maybe one node and its neighbors, or a clique within the graph at a time. Here's a helpful overview from Zhu et al. Of the different types of graph neural networks. One of the most popular forms is spatial, so that you're going to have a convolutional operator that we'll define in a little bit, and then we're going to reason about the spatial relationship among our nodes. We're going to build that up from the basic graph, the vanilla graph neural network, and then we're going to bring in graph attention layers to then go beyond that initial capacity to improve the model performance. And GNNs can be thought of from a message passing perspective, where recent studies, for example, Gilmer et al. In 2017 and Battaglia et al. In 2018, managed to unify the different graph neural network variants you saw on the previous slide into a message passing paradigm. And neural message passing goes back decades to people that were looking at biological systems wanting to send information to each other in the biochemistry world. And we're going to think about this message passing as every neighbor node talks to each other by passing messages. And this may, in a directed graph, the messages would flow one way, and in an undirected graph, the messages would flow both directions. And our vanilla graph convolutional operator will work by first sending a message from each node to all other nodes. Each node will then aggregate that information, receive it, and then perform some. In the aggregation, you might be summing and then applying through a rectified linear unit. And this is going to look like, for a given node, the graph convolutional features at the next layer is going to equal the activation function, for in this case, a rectified linear unit, and then a summation over all nodes that are neighbors of node I. We have a normalization constant C sub ij, and then the node features of the neighbor itself. That could be, for example, in our scheduling problem, it could be the duration of the task that needs to be performed, and then some weighting matrix that's going to be learned. Yes, there was a question, will the slides be available after the presentation? Yes, we thank you, Jiwin, for answering. We do have the slides available on our website, the tutorial website that you're welcome to download. And more formally, the message passing perspective paradigm is going to define the edgewise and nodewise computation of a graph with a G with vertices and edges. And we're going to have edgewise a set of messages for an edge E at some layer T plus 1, which is going to be equal to some function mapping given two vertices information and then the weighting information of the edge itself at that previous layer. And then we can say U is going to be the source, E is going to be the edge, and then V is going to be some cost, distance, or weighting for our edge within the set of all edges. This message function will be used on each edge to generate a message by combining the edge features with the features of its incident nodes. And then we can also think about node-wise operations to create the features for the node at the next graph convolutional layer for a node V, which will again use here a feature reduction mechanism, such as in our case, we're using the summation and a rectified linear unit that will take in all of the messages that are being sent to me from my neighbors and reasoning about that and the information that I already had at that current layer. And then we'll have our update function. There are a few different tasks that I'm just going to quickly highlight that we can do with graph neural networks. First, we can have node level tasks where we want to classify a missing node's information to categorize the node in several classes. In this simple graph coloring problem, we just want to predict what color is going to be the gray node Each of these gray nodes is just supposed to be green or red. We can think about this for a scheduling problem of which robot should be performing the tasks, and the green nodes are performed by the green robot and the red nodes are performed by the red robot. And we can do node regression to predict a continuous value, and also node clustering to try to partition the graph. We also have edge level tasks, edge level classification and link prediction, which requires the model to classify edge types or predict whether there is an edge existing between two different nodes. This could be what you see on Facebook or Twitter to say that who you should follow, or whether you should be friends with somebody. We can think about this in scheduling as deciding, should there be an ordering within, if these nodes are two tasks, should one come before another, and should we predict an edge or a link between them to temporally enforce the ordering of one task before another. And we also have graph level tasks, graph classification, graph regression, and graph matching, all of which need the model to learn graph representations. You can see some interesting applications to computer vision where you might want to be able to extract features of an image that then can be used to form a graph, and then look at the graph itself to say, is this element within this image the same as an element within an object within another image based upon the graph that is extracted from that image. Within neural networks, or within scheduling problems, typically our graph level tasks are going to be more of reasoning what the state of the system is as a whole, rather than, or you could imagine as like creating a graph from scratch, a generative process, which we'll talk about in a minute. Here is that we want to actually be able to create a graph from scratch. You could infer a graph of building, say from a simultaneous localization and mapping framework, where you now want to have semantic labels for all the rooms, and then edges denoting how you can get from one room to another. There's also work by Stefanos Nikolaidis and Matthew Fontaine that I'd point you to, that are doing some interesting work in curriculum generation for human robot teamings that I think could be applied, modeled, and thinking about some of these deep generative models for complex processes for coordination problems. And in deep generative models of graphs, you can generate a graph by following a state machine. At each time step, you either add a new node to the graph, or select two existing nodes and add an edge between them. And that is essentially what we're doing today, although we're not really grounding or classifying that as a generative approach to graph neural networks, more as a sequential graph construction mechanism for scheduling. And graph generation, as we'll see here, and very much related to what we're doing, you can ask, do you add a node to an existing graph just with one node? If yes or no, then you can add another node. Then do you add an edge between them? And you can kind of build up this graph and then try to use something like behavior cloning, where you're trying to, through supervised learning, to mimic the generation process of from a supervised learning data set of existing math graphs that you might want to create. Then there's a few ways that we can think about training these graph neural networks. First, a supervised setting, where you want to, in the node prediction task for scheduling, if we have instances of tasks that need to be assigned to robots, we can look at existing solutions and then try to predict which node will be assigned to which robots. We can think about a supervised, semi-supervised setting, where you have a small amount of labeled data and then a large amount of unlabeled data. And you could say in a test phase, the transductive setting might require the models to predict the labels of the given unlabeled nodes, while the inductive setting would provide new unlabeled nodes from the same distribution to infer. And most node and edge classification tasks are semi-supervised. Most recently, a mixed transductive inductive scheme is undertaken by Wang and Leskovich in 2020 and Rossi et al. In 2018, kind of creating a new path towards the mixed setting. We also have unsupervised setting, where you might want to do some kind of clustering on your graph, and then reinforcement learning, which we'll look at today. Here's some helpful survey papers that I would point you to. This is available in the slide deck that we sent, that is on our website. There's also some very helpful Python packages. DGL is one that we use extensively, the dgraph library. There's also PyTorch geometric and spectral. And companies are now looking and recruiting for people specifically who have expertise in these packages Just as a word of advice, some of these examples, for example, DGL, in the time that we've been doing our research, they've actually been coming out with new, better models, optimized structure. And so sometimes we found ourselves having to do something ad hoc on our own. And then some months or a year later, DGL actually comes out with the implementation itself. So we really are at the cutting edge of what these systems can do. And so these approaches have standardized some things, but there is still a good bit of work that's coming out that isn't fully implemented yet. And we'll see more of using these systems in our coding session when JUN takes over soon. So next, let's move into solving multi-robot coordination problems with graph neural networks, the exciting part. So I'm going to divide this up into 7 subsections. First, we're going to introduce simple temporal networks as the basis for our graph reasoning. And we'll talk about how do we construct a graph neural network, how do we train one in our Markov assistant process setup. We'll then cast this as an imitation learning via Q-learning setup, so we can actually learn from domain experts or an exact solver on small problems and then scale up that representations to large problems. We're going to try to improve the computational efficiency through a simplification trick that we have for our graph, for our simple temporal network and embedding or encoding. We'll add graph attention to improve the performance. We'll share some results once we get through that, and then we'll look at more expressive heterogeneous graph neural networks. First, simple temporal networks are ubiquitous in modeling multi-robot task allocation and scheduling problems. A simple temporal network is a directed edge-weighted graph with a set of vertices V and edges E. I would refer you to Mashetola and then also Rena Dechter et al. For their kind of foundational work back in the 90s on these simple temporal networks. Each node, V, will be represented as an event-related time point, so the start or the finish of a task or some other element. Each edge will be labeled by a weight, and it's directed, and representing the linear inequality, x sub j minus x sub I is less than or equal to the weight a sub ij. So this relationship here, if I was the start of task 1 and j was the start of finish of task 1, this would say that task 1 can take at least no more than 10 minutes to be completed and no fewer than 6 minutes to be completed, as described by this inequality here. And note, it's a little bit awkward to think about negative going back in time. It's kind of like a double negative, but that is the convention that you can then use for like Dijkstra's algorithm, Bellman-Ford, or Johnson's algorithm to do kind of processing on these graphs and make it work. We can represent a scheduling problem as a simple temporal network, where here's an example with 3 tasks. Task 1, task 2, and task 3 with a start and finish node for each. Task 1 will take a deterministic 5 units of time, 4 and 3 for the remaining 2 tasks. We're going to add some constraints. The finish time of task 1 has to be less than or equal to 7 minutes, as described by this arc. And then there's a wait constraint requiring that the start of task 3 to be at least 2 minutes after the finish of task 2. So if you start at task 3, go backwards 2 minutes in time, that's when you could have finished, the latest that you could have finished task 2. The challenge for us then, for a robot that can only do 1 task at a time, is to figure out the disjunctive's temporal problem. Which order should the 3 tasks be performed to minimize some cost or the overall duration and satisfy my deadline and wait constraints? This is an NP-hard optimization problem and entails, do I put task 2 before task 3 or vice versa? Task 1 before task 2 and vice versa. And then also I didn't draw here that you'd also have to reason about whether task 1 and task 3 comes before or after the other. That's where the integer variables comes, that you have to make these discrete binary choices over the ordering of each pair of tasks. Well, it gets worse because you also have to know when to do nothing. So here's another example with 3 tasks. Task 1 is 5 minutes, task 2 is 2 minutes, task 3 is 3 minutes. And there's a wait constraint that task 2 has to be at least 3 minutes after the finish of task 1. And we'll have a deadline that the finish of task 2 has to be within 10 minutes of the start of task 1. Well, the optimal schedule here would be, let's do the first task, then let's jump to the third task while this wait constraint expires, and then we'll jump back and finish the second task. So that is very efficient, and the overall make span would be 10 minutes, 5 plus 3 plus 2. But what if we changed one thing? What if we made this 4 minutes in time instead of 3? Well then, unfortunately, we can't do the same ordering. Now what we have to do is task 1, wait for 3 minutes doing nothing, do task 2, and then complete task 3, and the make span's 14 minutes. I made this problem a little bit harder by saying that task 3 is a little bit longer. What I could have done likewise is to make the deadline and the wait constraint shorter, and that could have achieved the same effect. And in general, what you find is that you can reduce constraints or seemingly make them easier actually, and still actually find it much harder to schedule the problem. It's kind of an interesting nuance of these problems. And in general, it's very hard to know when to do nothing until after you've come up with your optimal schedule, having searched over all orderings. So we're going to have to reason about the disjunctive temporal problem and reasoning about when to do nothing. So let's talk about applying graph convolutions to construct a GNN to reason about a simple temporal network. We're going to have a given node, say node I, all of its neighbors, J1 through Jn, and each of those nodes has a set of features, and then we have weighted or edgewise information that we're going to pass in and aggregate, for example, summing and passing through a rectified linear unit or a leaky ReLU. We're going to go through an example for node F2, the finish event for task 2. We can assume that our features for each node are whether or not they're a binary indicator for whether it's a start node, and then the duration of the associated task. We can kind of trivially set up some some graph convolutional weight operations, node-wise information, a matrix, and then edge information as a vector. And then we can set up a normalizing constant that's based on how many nodes that you are neighbored with. This is the vanilla graph convolutional operator that I mentioned earlier that only reasons about nodes, but we really do need to reason about edges here. So what we're going to do is come up with a corresponding vanilla scheduling-based operator that looks at the node level information, applies some matrix multiplication to that, and then also looks at edge level information, looking at the edge relating nodes j and I, summing over all neighbors j in the neighborhood of node I, and then we have our normalizing constant here, passing that through an activation function to then get the features at the next layer. So let's look at the node for finish time of task 2. We can look at the neighbors, which here are F0, S2, and S3. We can pass the features in for those 3 nodes here, along with the weight, the edge weight information. Here's our graph convolution operator, where the teal is used for the node features and then pink for the graph for the edge information. We then create our terms, just expand out the summation for each of our 3 neighbors. We can apply our graph convolutional operators. Note that the edge information for the finish node here is 0 for everything, so that term goes away. And if I've done my math correctly, you would then get out the new feature vector for, excuse me, I believe that should say F2 instead of S2, would be 4.6 repeating and then 10. Whereas when it started, HF of 2, just to kind of check, was it a start node? No. So this would have been 0. And then the duration of the task would have been 4. So now it's this new information here. Well, we can also apply multiple convolutional layers where we have the node feature information that we hand defined from the beginning at the 0th level, and then our new features at every layer L+1 takes in the information at level L, always uses the base information for the weights, and then apply hierarchically multiple graph convolutions. And this allows us to then create high-level feature information. Worst case, if you wanted to actually pass messages across an entire graph and the graph was incredibly sparse, you might need up to, on the order of the number of nodes, number of rounds of message passing or graph convolutional layers to make this work, to have every node talk to every node. But in general, for reasonably sparse graphs, you can find literature people recommend about 3 rounds of message passing. So after we do our message passing, we're going to get out a vector of features, a vector of vectors for each of our nodes, 1 through the number of total nodes. For example, I plugged that information in here. And then we can think about it in overall graph embedding, which would be the average embedding for each of our tasks. Now, it's important to note that averaging does lose information. We'll have a better approach later with heterogeneous graph neural networks. An example task that we might perform would be to rank which task should come first. One approach would be to connect a regular neural network output layer to make a prediction. This would look like taking our simple temporal network, passing it through our graph convolutional layers to get the graph embedding, the node embeddings out. Then we're going to do our averaging to get a graph level embedding and then append to it the task information start time of task 1, finish node for task 1, and similar for task 2 and 3. We can pass that through a fully connected layer and then get some probability that task 1, so this would be task 2, or then task 3 should be the task that you want to pick to come first. As prescribed here, we could do some kind of softmax operation over the concatenation of our graph level features, and then multiply that by some weight matrix theta. And we can train this to predict the correct choice, given a supervised learning set of examples, is some kind of cross entropy measure of, say, behavior cloning. We know what the task examples of the correct task to pick first, and we want to optimize the weights of our fully connected layers here, and then also our graph neural network layers here, to then correctly predict which task that we want to come first for a distribution of scheduling problems. But that's not what we really want to do. We don't want to just stop with deciding which task should come first, kind of in isolation of reasoning about the future consequences. We really have a finite horizon scheduling problem, a finite horizon optimization problem that will cast as a Markov decision process, where our state S is going to be the simple temporal network, a list of unallocated tasks, and also our current assignments of robots2 tasks. The action will be assigning a task I to robot J and adding the unscheduled task I to a partial schedule for robot J. A transition function will be adding edges into our simple temporal network to enforce the consequences of an action. So for an action, at time point t-1 that applied to task I to robot J, followed by an action at current time step of task P to robot Q, we would, if the two robots in these consecutive actions are the same robots, then the robots can't do the task at the same time. It's the same robot, you can only do one task at a time, so then I would have to add a constraint such the finish point of the earlier task would happen after the start point, happen before the start point of the later task. And then we have the value of the scheduling action in a given state, which might be a current estimate of the make span, and then we have some discount factor. We want to compute the reward. The example for a policy gradient-based approach for the reward might be saying a short-term reward would be the shortest path from F0 to S0, multiplied by -1 if we're not finished, and -10 otherwise. So what that does is it says that we really care about the make span of the final schedule, but we want to shape the reward a little bit along the way to kind of favor things that look like they'll have a shorter make span. And then we can estimate the Q value for a state action pair as the future discounted reward for a given scheduling rollout instance. So let's say we have a policy, pi sub capital theta, that we're going to assign at a time step 1 in our scheduled process, robot 1 to task 1. And then we'll assign robot 2 to task 3. And then at some point later, because both of our robots are now busy, we can assign at action time point 5, robot 1 to task 2. And we can think about the corresponding rewards for this first task is -5 because it actually doesn't impact the make span. The shortest path is from here to here is still -5. And then we still don't have any change to our overall make span. And then once we finish and assign robots to all of the tasks we see that the consequence in the resulting make span would be -9 because robot 1 has to do task 1 and task 2. Now you remember that we have a transition function that's going to modify our graph. And so for each action, if the robots assigned to adjacent actions was the same, then we have to add a temporal constraint saying that the latter assigned task has to come after the previously assigned task. And that's how we get our reward of -90 or our make span of -9. We can estimate our Q values for each of those scheduling actions. And then we could potentially apply a policy gradient-based update with our estimate of the Q function and then our scheduling policy pi sub theta. Now, how do we do that with the graph neural network? We can augment the graph for multiple robots now, where now we're going to have our node level features. First, is it a start or finish node, what the duration of the task is, and then a one-hot encoding that describes which robot has been assigned, and then it's just all zeros if no robot has been assigned to that task. We have to increase the size of the feature space representation for our graph convolutional operators. And here's the definition of a robot assignment, where this is the unit basis vector that's a 1 at element R and zeros everywhere else. We're going to take this and we can create our larger matrices now that encode our robot information. We can define what the node features would be for, say, the neighbors of node F1, and we can apply our graph convolutional operators as before, and then get an answer for what the node level feature information for F1 would be at the next layer of graph convolutions. And we want to provide a block diagram of what the scheduling generation process were at each iteration of our schedule. We're trying to figure out which robot can be assigned to which job and ordered in time using our graph neural network. So we're going to schedule through simulation to construct our schedule, where at times we're going to initialize our schedule construction at time 0. We're going to grab the set of available tasks that have been unallocated at time t. If the task is available, if there are no tasks available, then we will just go ahead and increment time. Otherwise, if there are tasks that could be scheduled, we're going to get our graph level embedding and then also task level embeddings and predict the probability that each of those tasks would be scheduled next. And then we ask, are there robots that might be available at that time to execute the task? If there's no robots, then we're going to go ahead and increment time. If there are robots, we're going to pick one of those robots and assign it to the task that we thought should be picked next. And then we will apply our transition function to add an edge to make sure that all of our robots can only do one task at a time. And then run an all pairs shortest path graph algorithm to make sure that the simple temporal network is temporally consistent, that has no negative cycles. And if it's not temporally consistent, then we will return infeasible. But if it is consistent, we then ask, are all tasks allocated? If yes, we'll return the schedule. If no, we'll increment time and then repeat. And then we would repeat by going back to look for other tasks available again to be executed. There are some nuances that I want to cover. How do you pick the robot? It's expensive to iterate over all actions as task robot pairs. So the number of tasks times the number of robots. Currently, what most of our work at the beginning did was just iterating over the tasks and greedily picking which robot was available. But in future work, some of the things that we've explored, and I encourage you all to look at the same, is like conditional policy decision-making, where you have one network that will look at the graph embedding and pick a robot given the overall graph embedding. And then given the robot that you want to schedule, could you then pick the task? So then your overall policy would be the probability of picking a robot given a state, and then picking the task given the state and the robot that you picked. And so you'd have two graph convolutional neural networks for those. And how do you know what tasks can be selected? And looking at temporal constraint satisfaction and all pairs shortest path graph algorithms, I would encourage you to look at a deeper dive on simple temporal networks outside of scope of today. I refer you to Machedala et al., Morris and Sermadinos in 1998 for reformulating temporal plans for efficient execution. I share with you one way that you might do this with an algorithm like reinforce. The way we actually did it, though, because we found it much more advantageous, was to do imitation learning with expert demonstrations. Why would you not just do it directly via reinforcement learning? Well, for these scheduling problems, it's a very large state space. And most of the problems that you randomly generate solutions for, or most of the solutions you randomly generate, are actually infeasible. So the reward function for any infeasible schedule that I didn't mention earlier, we could set it to be negative infinity, the worst possible case. And so if your network is just constantly getting the same reward and it's always bad, it's going to be hard for it to learn. So we could do imitation learning, or we could get examples of optimal schedules from some experts, some Oracle. And we could get those expert schedules from an exact solver like Gurobi or Cplex, giving a solution to the integer program on small scale problems, and then use the scalability of the learned representation to non-parametrically scale that up to solve larger problems. There's some nuances with using quote unquote experts. This is Garry Kasparov, who is a world-renowned chess expert, who you may know for infamously losing to Deep Blue, I believe it was called. So I use that to motivate this study by Bill Illich et al. In 2008 that looked at expert decision-making for humans and set them up, these expert chess players, to win in 3 moves. But they changed one thing about the board so that you couldn't achieve a checkmate in 3 moves. Well, this 3-move sequence was known to every chess expert as something that you should have habituated. And the researchers asked the experts to find a solution that would require 4 moves and require you to look somewhere else across the board. Well, what they did in a think aloud exercise is that the experts would say, I'm searching for novel options. But what the experts actually did was use their eyes were tracing out the same 3-move sequence over and over again. This is the Einstein effect, that these experts are habituated into wanting to make the same thing happen that they know should happen, but it can't happen. They have a hard time breaking outside of these prescribed mental thought patterns. But more importantly, there's this disconnect between what an expert says he or she is doing and what the expert is actually doing. So this is why we don't actually listen to human scheduling experts typically and ask them for advice on how do we generate our schedule. What we do is we either get examples from factories of good schedules, and we can improve upon them by using a queue function, say, or what we just rather do is define what the scheduling problem is and then ask Gurobi or Cplex to solve it for us on small problems and scale it up to larger problems. If there are experts, as I mentioned, that are available and solutions are enough quality, we can use their schedules for imitation learning. Otherwise, we could use some branch and bound search methods like in Gurobi or Cplex. It is optimal, but it's relegated to smaller scale problems. And the challenge here is that if you have a convex optimization problem, but then you add these disjunctive constraints or integer information, you now have to actually search over the individual integer solutions that you might have. There are LP relaxations and techniques to improve upon this, but fundamentally it is an NP-hard optimization problem. What we can do is have graph neural networks to learn a representation on small schedules and extrapolate how to solve larger scheduling problems. So again, we're not going to do this via RL. We are going to do it via imitation learning. And there's 2 approaches that could be scaffolding for our RL-based or imitation learning framework. One would be policy gradients, where we want to train a policy to mimic our expert, and we could weight that by the quality of the solution. Or we could do it as a queue function, where we have our estimate of the queue function, and this is the Bellman residual, essentially. What we're going to do is we actually find it's better to do the queue function for deterministic problems, because we can actually reason about the quality of the resulting schedule, and it seems to be more efficient. But for stochastic problems that I'll briefly mention later, we typically find that doing policy-based learning or reinforced might be better, and also helps kind of bias you towards being safer or to be more feasible when you have these stochastic elements of your scheduling problem. So we're going to define an expert loss, where we want our neural network to be able to predict the quality of the schedule that results in each state of our graph construction, and then the action that we apply to assign a robot to a task and adding constraints into our graph. And then we're going to add a counterfactual loss. So this was kind of inspired by some prior work that we had seen in related problems for imitation learning in JUN define this in our scheduling problem, where we're going to say that for every other action other than the one that the expert took should be at least some Q naught worse than our estimates of the quality of the schedule now. So everything other than what the expert did, the Q value should be worse for it. And then our full loss will include the expert loss for trying to accurately predict what the efficacy of our scheduling actions are, plus making sure our counterfactual actions are worse, and then some L2 regularization. And we recall that the way that we talk about states and actions is really a concatenation of our graph embedding and then the task level embeddings. But we still find that there's not enough VRAM in all the world for some of these large problems. So we need to simplify our graph. And in the worst case, the current approach that we showed you so far requires O of the number of tasks to call, it's actually worse than that, is 2 times the number of tasks. It calls the all pairs shortest path algorithm. We're going to have to do this for every task that we schedule in the worst case. And the number of elements within the graph is 2 times the number of tasks. Johnson's algorithm is relatively fast for sparse graphs, but it does add up. And after each column, we need to pass the graph through our graph neural network, with each layer requiring O of V squared operations. So can we do better? And under the homogeneous robot team setting, where every robot is identical, completes tasks at the same time, the task duration is deterministic without knowing the actual assignment. So we can develop a novel simplification trick to reduce the model complexity. So first, we're going to take our graph and run Johnson's all pairs shortest path algorithm to find the minimum distance graph. You could also do Floyd-Warshall or any APSP algorithm. We're going to, the result will be this matrix of source to destination nodes, and then the associated shortest path. And then we're going to remove all of the finished nodes except for the final finished nodes from this distance graph. And the resulting graph will just be start nodes, and then the overall finished node is a compact and graph representation, and with some nuances of information we have to keep track on the side. All the information that we need is preserved within this graph representation. But it has about half the nodes and still reserves all the necessary temporal constraints. And then each task can be represented by a start time node as the start nodes, with the task duration now serving as its node feature. And so then the disjunctive temporal problem is deciding the ordering of our start nodes. We have to modify the weights. They're not just 0 now, because the duration of the task now has to be encoded into this information as well. Next, let's bring in graph attention operators. So this was our vanilla graph convolutional operator without the scheduling formulation. And this normalization constant is static for each of the message aggregation procedures. A better solution that Zhou and Wang found would be to use attention. So we can replace 1 over Cij with some alpha ij that would then determine how do we focus or prioritize our quote unquote attention on each of our neighbors. And we're going to do this with a softmax over a Ricci-Rayleigh of some temperature coefficient, and then concatenation of our feature information and then our neighbor's feature information. And then just for convenience, we can find the Rayleigh and Ricci-Rayleigh here, and our concatenation operation is the double vertical bars. And a graphical representation of this information flow would look like our node information here that we're convoluting over, all of our neighbors, and all of that pairwise gets fed into essentially a neural network dense connected layer. Out of that, we then apply the softmax for all those operations, and then we get our attention coefficients pairwise. These attention equations within our graph convolutional operators then are going to look like, now we add in these attention coefficients through our softmax, and then we weight our our message aggregation information through the attention coefficients before we output our new node information at the next level. And I've included the equations here for completeness now, where the vanilla graph convolution operator was just the node information and the edge information being multiplied and then aggregated, and now we're weighting it by our attention-based information here. The GUN and I published a paper in IEEE Robotics and Automation Letters back in 2020. That was the first solution approach that we had for this. And we benchmarked our algorithm on small tasks, small data sets with 16 to 20 tasks, medium with 40 to 50 tasks, and large scale tasks with 80 to 100 tasks for 2, 3, 4, and 5 robots. And we compared to earliest deadline first based scheduling, a ubiquitous heuristic. Tercio, the algorithm that I shared with you for my master's thesis a number of years ago, kind of an earlier formulation that we had of RoboGNN, and then also in Gurobi. And unexpectedly, for the number of problems solved, for smaller problems, Gurobi is able to solve almost all of them. Now, the computation time here is shown in seconds. And so we find is that Gurobi is taking up to 752 seconds to find the optimal solution for 2 robots. Whereas our RoboGNN in this case is the baseline that we have now. For RoboGNN, we're able to do almost the same, maybe about 5 to 10% fewer problems solved, but in 2 orders of magnitude faster. And we're way better than Tercio, my prior work, or EDF. And it is a humbling, but also incredibly exciting experience as a assistant professor for your new grad students to completely destroy your prior work. So hats off to Jaywin for doing that. And this scales up nicely. Tercio very fastly falls to be able to schedule almost none of the problems of interest, whereas our RoboGNN scheduler is able to maintain above 80% on all the problems configurations that we tested. Note that Gurobi would time out at 3,600 seconds. So that's why it's down here and it says 3,600. It was timing out for all these, and the solution quality would then be lower because it may not be able to go to find the optimal solution. So this was a really strong advancement in the state of the art. But it had a couple of weaknesses and expressivity that we want to now relax with heterogeneity. So first, our robots were all perform tasks at the same rate, and then we also only had task edges. So we have heterogeneous graphs that started to be pursued more recently with a reference to Zheng et al. In 2020 that looked at this for classification in social networks of authorship. So heterogeneous graphs are going to learn per edge type message passing and per node type feature reduction mechanisms. So instead of having a homogeneous graph where everyone is an author and related, have you published together, you're trying to predict is there a missing author or who this person is, we can actually think about graphs having authors and papers and conferences where you published, and then edges relating semantically differentiated messages being passed along the corresponding edges. And so we took advantage of this in developing ScheduleNet that was published at RSS in 2020, then we extended that in Autonomous Robots in 2021. We're going to extend our simple temporal network formulation into a heterogeneous graph where now we're going to have our STN, but also robot nodes, location nodes to encode location and resource or physical constraints. And we're going to propose a novel heterogeneous graph attention network ScheduleNet that learns per edge type message passing and per node type feature reduction mechanisms on this graph. So again, we have our simple temporal networks with our temporal constraints, but now we have robots and the shared resources, locations that are all going to be passed into a heterogeneous graph construction. That will then give us a heterogeneous graph with input node features. We're going to put that through heterogeneous graph attention layers to then get Q values for each of our tasks to then guide the schedule generation process. We're going to now think about this and specifically with location and physical constraints, that a task now actually requires multiple robots or multiple agents to perform it. You can think about physical locations or tools being a form of a robot. So that does increase the complexity of the scheduling problem. So ScheduleNet with homogeneous robots. First, we're going to do this with homogeneous robots. Every robot performs tasks at the same rate, but then we're going to move to heterogeneous robots shortly. So we're going to make every component of the graph problem a node. We're going to send a simple temporal network with robot and location resource nodes. And we're going to move towards a fully convolutional framework where we don't have any kind of output fully connected layer. We're going to do this with state summary nodes and Q value nodes. We're going to add attention like we did before. And so here's our metagraph. So, well, beforehand, all we had was tasks with their temporal constraints relating them. But now we're going to have tasks located in a specific location, some proximity information about how the locations are physically distributed across the world or our factory environment. We're going to have robots. Tasks are assigned to robots, and robots can be in communication range with other robots. And then all of the task, robot, and location information will be aggregated into a state feature. And when assignments from a robot are made to a task, ground are conditioned on the state, that will be passed to a Q value node that will then predict the Q value for each robot task assignment. The graph can be also visualized here. We have task nodes in cyan, location nodes in blue, robot nodes in lavender. We have a purple state node, and then we have Q value nodes for each of our decision points that we're going to make. Our heterogeneous graph attention layers are going to have per edge type aggregation results computed first, and then merge to attain the destination node's output features. So there's going to be a lot of equations here. I'm going to move quickly because we don't have time to go over all of the elements, but they are here for completeness. So again, we're going to look at for each task. We can think about our graph convolutional operators with attention. We can think about the same for robots, for locations, and for states. And then we have the general prescription of how we compute the attention information as a softmax over Riku-Lelu of the associated information. And we note that this is going to depend on the destination node type, whether it's a communication near or state in based matrix multiplication for the semantically differentiated edges. And then here's kind of the complete list. We applied this to a homogeneous robot case with 2, 5, and 10 robot teams on small, medium, large, and extra large tasks. We were able to scale this up larger with our simplification technique, better GPUs, and also our heterogeneous graph convolutional layers, making this fully convolutional. We have our metric for the proportion of problems solved within a certain optimality ratio, and compared again to our RAL, paper, EDF, Tercio, and Gurobi. We find that just on the 10 robot case, the 2 and 5 robot cases look similar, that we're in blue able to solve much more problems than our prior approach, as well as Tercio and EDF for small, medium, and large problems. Now note that Gurobi is implicitly shown here. Gurobi would be able to get hypothetically a 1.0, the optimal solution. But for large problems, Gurobi wasn't actually able to solve these problems. About 5% of them, our approach actually got better solutions than Gurobi. So Gurobi wasn't able to solve them to optimality. And we look at the extra large problems. There's also a subset of problems that we are able to solve the Gurobi better than Gurobi, and then we're able to solve about 80% of the problems that Gurobi could solve within an hour of timeout. And then in computation time, though, we are able to improve upon Gurobi between about 1 to 2 orders of magnitude, depending on problem size. Note that this is about 2 orders of magnitude here between us and the exact solution approach. Here, this is actually solutions not being solved to optimality. Gurobi is just timing out in an hour. And we see this advantage. Now, interestingly, where you see it terminate, for example, earliest deadline first can't even solve some of these larger problems. Our prior state-of-the-art approach couldn't solve the largest problems and is slow. And also you see a commensurate computational time increase for EDF. So we are treating a little bit, not perfectly optimally solving the problems, but we're treating a little bit of optimality for a great improvement in computational performance and substantially improving upon prior state-of-the-art. We can also, this is one of the most exciting findings that we have, is that we can apply this to application-specific objective functions. So we can change the objective function now instead of minimizing make span. Now let's say we want to minimize the weighted tardiness of the task completion time. So every task has a predefined weight CI that says how important it is to finish it quickly. And we can find that we can automatically apply our Q-learning framework and then without substantially changing the graph neural network architecture, now we can solve those problems as well. So scheduling that started job perform the prior, so a heuristic baseline when the ratio became larger, resulting in overall better performance. So a strong improvement there. But workers are not all homogeneous. So we don't just have workers that have a specified rate for which they all complete the tasks in the same way. we're quite diverse. So we can have diverse robots, diverse humans, and everyone has the unique rate for how quickly they can perform a robot. And we also say that some agents can't even perform some tasks. A nurse or a doctor may not be able to build a building, and or a plumber is not going to then be able to do open heart surgery. That happens in manufacturing with certifications as well. So we want to reason about this heterogeneity within our team. So now we're going to expand for our autonomous robots paper, ScheduleNet with heterogeneous robots, where the duration of the task depends on the robot which it is assigned to, and for scheduled tasks, duration is given by the assigned robot. For unscheduled tasks, we can only use a relaxed set of bounds, a minute and a max duration among all robots. We don't know how long the task will take until we made the assignment. And so we have to include that possible the contingencies for different durations of the task here and within our metagraph. And to preserve all the information needed, we'll extend the set of task node features to include multiple descriptive statistics about the distribution of the mean and the variance of the distribution of our team for performing each task. And then we'll add 2 new edge types between nodes of unscheduled tasks and robot nodes. Now, we're also going to handle 2D proximity constraints. Where only connect locations that fall within a minimum allowed safety distance to represent proximity constraints, and instead of connecting the location nodes with every other location node. And the edge type associated of location to nearest or near and then another location will exist, but although shares the same name as in the homogeneous graph case, just to note, but it now is encoding 2D constraints. We'll also do a graph tension layer, which I'll just include here for completion. Just to note that the feature update equation of robot nodes is going to change to account for this new information that we have in the graph for the heterogeneity in our robot cases. And again, we see strong performance for some of the smaller problems. For this heterogeneous robot case that Tercio is specifically designed for, it is able to outperform our approach for some of the smaller problem instances. But as we scale up to medium-sized problems and large problems, Tercio can barely solve 5% of the problems, where we're getting up to about 30% of the problems find. So really exciting, strong performance against prior state of the art. And then for the largest problems, we're at 24% of problems from our database solved, whereas EDF and Tercio were able to solve virtually none of those problem instances. So this work was in autonomous robots. And then in computation speed, some of the fastest advances we had. So now we have a computational speed that's about the same as EDF, a very simple heuristic that was slowed down, unfortunately, by a lot of all pair shortest path graph computations and iterating over combinations. So we're doing much faster than even simple heuristics at this point, which was really cool. Here's a couple of cool videos that you can view by clicking this link for deployments. We have these scheduling operations within the Robotarium at Georgia Tech for homogeneous and heterogeneous robot cases. Takeaways for what we shared with you today is that we're able to outperform prior work in terms of optimality and feasibility when you look at certainly computation time, training off computation time and optimality, and we can have better scalability. Up to 200 tasks, 10 robots, and 10 locations. It's a flexible framework where we can change, adapt to changing objective functions. We're getting an order of magnitude speed up versus an exact method at least 10 times versus Gurobi. A little bit of ongoing and future work. Aircraft maintenance scheduling is an exciting area of work that we have going on, where we want to look at preventing and reducing the adverse effects of aircraft part failures, and then maximize aircraft availability and picking the right repair team for the right maintenance job. So GRN developed this scheduling environment, AAME, where we have different types of aircraft that are flying, they break, and we have a heterogeneous graph attention mechanism, and we're using a form of reinforcement learning to then optimize, do we ground a plane and fix it before it breaks, or do we wait for it to break? Here's a metagraph where we have crews, planes, and state aggregation, and our decision nodes. And different for this, we actually need to look at policy gradient-based approaches because of the stochasticity within the problem itself. And we looked at profit-based objectives and then revenue-based objectives. And I don't have time to go over all of our results, but roughly speaking, that a 1% improvement in our approach Here we're about 15% improved over waiting until your plane breaks and then doing some kind of weighted queuing here. Every 1% improvement, it's about $657 million of revenue increase, and then our approach would achieve about a $9 billion improvement in revenue over corrective scheduling for a specific set of, for a large commercial carrier of aircraft. We've also been looking at graph neural networks for multi-agent systems, where we can have like kind of a straightforward application of graph neural networks where our agents are nodes, and then how they communicate within a finite communication range, and the decentralized POM-DP would be described with the edges. And the message passing computation of the graph convolutional layers aligns naturally with communication in multi-agent systems, and the decentralized execution as each node operates on local information and is scalable and the number of nodes. We've applied this with some of my students, I see Siraj, Rohan Palaja, and others, to look at heterogeneous teams, our composite teams of perception and action agents that have to work together to detect and track wildfire propagations to protect houses and hospitals, and then action agents who can take water from the lake, say, and then go and douse the fire out. So you have to figure out how do they do this, and importantly, when do they communicate sensed information, who do they communicate with, and how do they stay in touch with each other within communication and bandwidth limitations. We developed the HETNet as a heterogeneous graph attention network for class-specific encoder-decoder communication channel and a centralized training, decentralized execution framework, where we actually learn binarized communication. So this is a complicated figure that I'll gloss over for time, but basically we're using an LSTM to encode local observations and graph neural network then to figure out what information I should send to my neighbors. Maybe I know something that they should know, or I want to tell them something about what I'm doing. And we're going to actually use a Gumbel softmax to figure out how to communicate in binary, so we can send binarized communication messages that are readily compressed, very, very compressed information. We looked at this across 3 domains. A homogeneous environment where predator agents are all trying to find a prey agent. The sensing range is shown here, kind of in this grayish color. A predator capture version for heterogeneous agents where the perception agents can find the prey, and then the capture agents have to then be told where to go because the capture agents can't see anything. And we also had a grid-rolled version of a propagating fire where the perception agents have to detect and track the dynamic fire, and action agents have to go and put it out. We found for all 3 of those domains improvement over prior work. For the first domain shown here, we're able to get an 8.3, whereas prior work was the best approach was ComNet at 8.97. For our heterogeneous domain, we had a 9.98 number. These numbers are the number of time steps needed to complete or win the scenario. So this is about 10. Prior state of the art got to about 10.8 magic, but magic is technically a centralized algorithm, whereas we are decentralized in execution. And then for our most complicated fire commander environment, we were able to get about a 5-fold increase, a decrease in the amount of time required to completely extinguish all the fires. And my favorite chart is that if you kind of do a sensitivity analysis looking at the amount of information and the binarized message channel that you allow HETNet to send, we're able to compress it down to like 64 bits, 32 bits, and down to about 16 bits of information before our performance is comparable to that of a centralized approach. And so this is enabling us to achieve a 200-fold reduction in the information required that we have to share across our team. That very much helps for low size, weight, and power restrictions on distributed robotic platforms. Some challenges and open questions. We have multi-robot coordination problems. In production environments in the real world, we have machine breakdowns, unexpected releases of high priority jobs, and uncertainty in the processing times, and learning to pick. So those are really challenging. The stochastic aircraft maintenance problem is probably the most difficult problem that we've worked on so far because of the stochasticity. Reinforcement learning just doesn't like it. So there needs to be more work there. Learning to pick the robot function, as I mentioned earlier. So picking robots and tasks, not just picking tasks and then using greedily an available robot. And also accounting for human workers and the stochasticity and time varying aspects that come with how humans interact with robots. And I think there's also more work with graph neural network modeling to help handle complexity. How do we batch of heterogeneous graphs and distributed training for large scale problems? So with that, I'd like to thank you, and I'd like to also note, Jaywin, thank you. Thanks, Jaywin, for also helping me prepare this presentation. And with that, I'll be happy to take any questions, and we'll switch over to Jaywin for the coding session. All right. While Jaywin gets set up for the Google Collab, if anyone needs to take a bio break, this would be a good time, and then Jaywin will get started in just 1 or 2 minutes.